In this video, we are going to look at how the boiling point of a solution can change depending on the solute particles that are present. And that is called the boiling point elevation. The normal boiling point happens when the vapor pressure is equal to the atmospheric pressure at the surface of the liquid. And the boiling point is going to be different for every different type of molecule. When you add a solute to your liquid, it is going to increase the vapor pressure. And if we increase the vapor pressure, then that means that we're going to also increase the boiling point of a liquid. So the boiling point elevation simply states that if you add a solute, increases the boiling point of a liquid. And we can actually calculate that. Delta TB, which is the boiling point elevation, is equal to KB times lowercase italicized m, where m is the molality, it is the moles of solute per kilogram of solvent. So this is different than molarity because we're dealing with kilograms of our solvent, not liters. KB is the boiling point elevation constant, and it is going to be different for each solution. All right. And so this should be solvent. There we go. So each solvent is going to have its own boiling point elevation constant. So what we're really doing here is looking at why do we have a change in boiling when we add different solute particles. And if we add this solute or that solute, how is the boiling point going to change? Now, remember, the molality of the particles is going to be equal to the moles of your solute particles times the number of solute particles. So you really need to make sure that you know how to use your solubility rules and calculate the number of solute particles that are present in a solution. So let's look at an example. If we add 0.45 grams of potassium cyanide to 10 milliliters of water, we can determine what the boiling point is. So in order to do this problem, I am going to use the equation delta TB is equal to KF times the molality of the solute particles. In order to calculate the molality, I need the moles of solute particles times the number of solute particles divided by kilograms of my solvent. Ooh, what are you doing, pencil? There we go. There we go. So the first thing I'm going to have to do is change my grams to moles. We need that in moles in order to calculate the molality. So I can use the molar mass in order to do that. 0.450 grams of KCN times, now I need to calculate the molar mass. And when I do that, I get 1 mole of KCN over 65.12 grams of KCN. Now my grams cancel out and I'm left with moles of KCN. When we plug this into our calculators, we get 0.00691 moles. I also need to calculate the kilograms of solvent. I have 10 milliliters of water. And I know the density of water is 1 gram per milliliter. Remember, that's only the density of water. If you have a different solvent, you need to use the density of that solvent. And then I can change this to kilograms. And there are 1,000 grams in 1 kilogram. So if I have 10 milliliters of water, that is also equal to 0.01 kilograms. When I plug that into my equation, I'm going to get my 0.00691 moles. And I need to multiply that by the number of particles in solution. Now, when KCN gets put in water, then it is going to completely dissociate. And I know that because of the N rule. Potassium is in group 1, just like sodium, so it's going to completely dissociate. And it's going to dissociate into potassium ion plus cyanide. So that means there are 2 particles present. And then I can take that and divide it by the kilograms of my solvent, which we calculated to be 0.01. When I plug this into my calculator, I get 1.38 molal. Now I can take that number and plug it into my delta TB. So KF, oh, sorry, this will make more sense if we put KB because we were talking about the boiling point elevation and not the freezing point depression. So KB, the constant is 0.512, and my units are degrees Celsius per molal. And I can multiply that by the molality that I just calculated, which is 1.38. Notice my units of molality cancel out, and I'm left with units of degrees Celsius. When I calculate this out, I get 0.708 degrees Celsius. Now, this is very important. This is not the answer. The boiling point of this solution cannot be 0.708 degrees Celsius. That's almost freezing. And boiling for water is 100 degrees Celsius. So I know it has to be more than 100 degrees Celsius. This only solves for the change in the temperature, not the boiling point. So in order to get the boiling point, I need to add the normal boiling point, which is 100 degrees Celsius for water. And that gives me 100.708 degrees Celsius. So that is going to be my final answer. Notice my final answer is not the 0.708. That just would not make sense.